Hey everyone, and welcome to another deep dive. Today we're going to be exploring the world of deep reinforcement learning, or DRL for short. We've got a really cool mix of stuff to dig into today. Classic textbook, which is always fun, and a couple of articles that explore some of the latest applications and advancements. So get ready, because we're about to demystify DRL, explore its mind-blowing potential, and uncover why this cutting-edge AI matters to you.
I'm excited to dive in. What I find really fascinating about DRL is that it combines the power of deep learning with the goal-oriented nature of reinforcement learning. Essentially, we're talking about training a digital student to solve real-world problems.
So it's like we're creating AI that learns by doing. That's a pretty cool concept. Could you maybe give us a simplified breakdown of how this whole thing works?
Absolutely. Think of it like training a dog. You reward them for good behavior, and you correct them when they do something wrong. In DRL, we have these things called agents, which are basically our AI learners. They interact with an environment, take actions, observe the outcomes, and receive rewards or penalties based on their performance.
Okay, so it's like a constant feedback loop where the agent is trying to figure out the best actions to take to get the most reward. But what exactly is deep about deep reinforcement learning?
That's where the deep learning part comes in. These agents use powerful deep learning models, often neural networks, to process complex information from their environment. This could be anything from visual input like images and videos to sensor data, or even more abstract concepts.
So these neural networks allow the agent to kind of perceive and understand its surroundings. Then it uses that understanding to make decisions and learn from its experiences, sort of like how our brains work.
Precisely. And the reinforcement learning framework provides the structure for this whole learning process. The agent's decision-making strategy is called a policy, and it's constantly being refined as the agent learns.
So policy optimization is basically about fine-tuning the agent's decision-making process.
Exactly. Let's say you're training a DRL agent to play a video game. The policy would determine what actions the agent takes in different situations within the game. As the agent plays and learns, the policy is updated to improve its performance, making the agent a better gamer over time.
Got it. So I think I'm starting to grasp the concept here, but what can these DRL agents actually do in the real world? You mentioned video games, but what about practical applications?
Now that's where things get really exciting. DRL is being applied across a wide range of fields, from robotics and autonomous driving to finance and healthcare.
Robotics. That's something I think a lot of our listeners would be interested in. Are we talking about robots that can actually learn to perform those complex tasks we always hear about?
Absolutely. Let's take the example of a company called DeepSeek and their R1 model. They're using DRL to train robots for tasks like assembling furniture.
Wait, robots putting together IKEA furniture. Now that's something I can get behind. Tell me more.
Well, traditionally, programming robots for these intricate tasks was incredibly complex and time-consuming. But with DRL, the robot can learn through trial and error, much like a human would, by actually practicing the task and receiving feedback.
So it's like giving the robot a virtual training ground where it can experiment and improve its skills. Does that mean we can finally say goodbye to those frustrating assembly instructions?
That's the idea. DRL aims to make robots more adaptable and capable of handling those complex tasks without requiring explicit programming for every single step. In the case of DeepSeek's R1, the use of reinforcement learning significantly minimizes the need for human intervention during development, which also makes it way more cost-effective.
That's pretty amazing. So DRL is not just making robots more intelligent, it's also making them more affordable and accessible.
Exactly. And the applications extend far beyond just manufacturing. DRL is being used to train robots for things like surgical procedures, search and rescue operations, and even exploring hazardous environments.
Now that's what I call cutting-edge AI. But I also remember reading about DRL making big splash in the gaming world. Wasn't there a DRL agent that beat a world champion Go player?
You're talking about DeepMind's AlphaGo, and yeah, that was a historic moment in AI. AlphaGo used DRL to master the ancient game of Go, which is so complex it was long thought to be beyond the reach of artificial intelligence.
Wow, so these DRL agents can fold laundry, perform surgery, and outsmart humans in strategy games. It's like the ultimate test of intelligence.
It is a truly remarkable demonstration of DRL's ability to learn complex strategies and make decisions in challenging environments. And AlphaGo wasn't just a one-off success. DRL agents have since conquered games like chess and even the incredibly intricate real-time strategy game StarCraft 2.
So these DRL agents are learning to think strategically and outmaneuver human opponents. That's pretty impressive. But how does this translate to practical applications beyond the gaming realm?
That's a great question. The skills these DRL agents learn in games, like strategic thinking, planning, and adapting to dynamic environments, are highly relevant to a wide range of real-world problems.
Okay, I see what you mean. So the knowledge gained from gaming can be applied to things like autonomous vehicles.
Exactly. Self-driving cars need to navigate complex environments, make real-time decisions, and respond to unexpected events, much like a DRL agent playing a challenging video game. DRL provides a powerful framework for training autonomous vehicles to handle these complexities safely and efficiently.
So it's like giving the car a brain that can learn from experience and adapt to those ever-changing road conditions. That's both incredible and a little bit mind-boggling.
It is. And the applications don't stop there. DRL is also being used in finance to optimize investment strategies, in healthcare to personalize treatments, and even in energy management to optimize energy consumption.
Wow, it seems like DRL is popping up everywhere. It's like this hidden force behind so many technological advancements. But I'm curious, with all this talk about AI learning, are there different types of DRL algorithms that are used for different applications?
Absolutely. There are a variety of DRL algorithms, each with its own strengths and weaknesses, and researchers are constantly developing new ones to address specific challenges. Let's take a look at a few of the key algorithms that are driving the DRL revolution.
Okay, let's dive in. This is where it gets really interesting for me.
One of the foundational algorithms is deep Q networks, or DQN. It uses a deep neural network to predict the value of taking different actions in a given situation. Imagine the agent asking itself, if I do this, what's the likely outcome? And how good will that outcome be for me in terms of achieving my goal?
So it's like the agent is constantly evaluating its options and trying to choose the path that leads to the biggest reward. That sounds pretty intuitive.
Exactly. And then you have policy gradient methods, which take a different approach. Instead of predicting the value of individual actions, they try to directly learn the best overall strategy or policy for the agent to follow.
So instead of evaluating each action separately, it's looking at the bigger picture and trying to figure out the optimal sequence of actions.
You got it. Some popular examples of policy gradient methods include reinforce, actor-critic, and proximal policy optimization.
It's amazing how these algorithms can mimic human-like learning processes, but in a more data-driven way. But I'm also curious about the challenges researchers are facing in the field of DRL. It can't all be smooth sailing, right?
You're absolutely right. DRL is a relatively young field, and there are still some significant challenges that researchers are working to overcome. One of the biggest hurdles is sample efficiency. DRL often requires massive amounts of data to learn effectively, especially for complex tasks. Imagine training a self-driving car. It needs to experience countless scenarios on the road before it can be considered truly reliable.
That makes sense. It's like giving the algorithm enough practice to become an expert. But are there other challenges besides just the sheer amount of data needed?
Another challenge is the balance between exploration and exploitation. The agent needs to try new things to discover better strategies, but it also needs to exploit what it already knows to achieve good results. Finding the right balance is crucial for efficient learning.
So it's that classic dilemma, do you stick with what you know or venture into the unknown? It seems like even AI has to grapple with that.
Indeed. And then there's the challenge of generalization. Can a DRL agent take what it's learned in one situation and apply it to a completely new scenario? This is especially important for real-world applications where unexpected events are bound to happen.
That's a crucial point. It's not just about memorizing patterns, it's about truly understanding the underlying principles so the agent can adapt to new challenges. That sounds incredibly difficult to achieve.
It is, and it's one of the key areas of focus in DRL research. Researchers are developing new techniques to improve generalization and make DRL agents more robust and adaptable.
It's fascinating how these challenges mirror the complexities of human learning. But before we get too deep into the technical weeds, let's shift gears and explore some of the real-world applications of DRL in more detail.
Sounds good. I'm ready to delve into some specific examples.
Great, because I'm particularly curious about how DRL is being used in the field of robotics. I think our listeners would love to hear more about that.
Excellent choice. Robotics is one of the areas where DRL is having a profound impact, and we can explore some fascinating examples.
So we were just starting to talk about all the amazing ways DRL is being applied in robotics. Can you give us some more specific examples?
Oh, absolutely. One area where DRL is really making waves is in grasping and manipulation. Imagine a robot that can pick up and manipulate objects with the dexterity of a human hand. This has been a long-standing challenge in robotics, but DRL is helping to make significant progress.
I can definitely see how that would be incredibly useful in so many industries, from manufacturing to healthcare. Are there any real-world examples of DRL being used for this kind of robotic manipulation?
Yes, there are. Researchers at OpenAI, for example, have developed a DRL system called Dactyl that can manipulate a Rubik's Cube with remarkable dexterity. It learned to solve the puzzle through trial and error, receiving rewards for successfully manipulating the cube. And what's really remarkable is that this learning happened entirely in simulation, and the system was then able to transfer its skills to a real-world robot hand.
That's incredible. So it's like the robot learned to solve the Rubik's Cube in a virtual world and then applied that knowledge to the real world.
It is a testament to the power of DRL to bridge the gap between simulation and reality. This kind of technology has the potential to completely revolutionize how robots interact with the physical world.
It sounds like DRL is opening up a whole new realm of possibilities for robotics. What other exciting applications are there?
Another fascinating area is locomotion, particularly in challenging environments.
Hmm.
DRL is being used to train robots to walk, run, jump, and even navigate complex terrains like stairs, rubble, and uneven surfaces.
So we're talking about robots that can move around in the real world with agility and grace. That's a far cry from those clunky robots we often see in sci-fi movies.
Exactly. DRL is helping to create robots that are much more adaptable and capable of operating effectively in the real world. One example that comes to mind is Boston Dynamics' work on robots like Spot and Atlas. They use DRL to train these robots to perform incredible feats of agility and balance. Oh, wow. I've seen videos of those robots that are unbelievably agile. It's almost eerie how lifelike their movements are.
It is quite impressive, and DRL is a key factor in their ability to move so fluidly and navigate those challenging environments. These robots can be used for a variety of applications, from inspection and surveillance to search and rescue operations.
It sounds like DRL is really pushing the boundaries of what robots are capable of. But what about those challenges we discussed earlier, like sample efficiency and generalization? How do those challenges play out in the context of robotics?
Those are definitely critical considerations. In robotics, collecting real-world data can be really expensive and time-consuming. So researchers are exploring ways to improve sample efficiency by leveraging simulation, transfer learning, and other techniques. Generalization is also a key concern, as robots need to be able to adapt to new and unforeseen situations.
So it's not just about training robots to perform specific tasks, it's about equipping them with the ability to learn and adapt on the fly.
Exactly. The goal is to create robots that are not just programmed to follow instructions, but can actually learn from their experiences and make intelligent decisions in those real-world scenarios.
That's a pretty exciting prospect.
Yeah.
It sounds like DRL is playing a key role in the evolution of robotics. But before we move on, I'm curious about one more thing. You mentioned earlier that DeepSeek's R1 model is more cost-effective because it requires less human intervention. Can you elaborate on that? Why is DRL making robots more affordable?
That's a great question. Traditionally, programming robots was a highly specialized and labor-intensive process. Engineers had to meticulously program every single movement and decision the robot made. This required significant time, expertise, and of course, cost.
So it was like writing a super detailed instruction manual for every task the robot needed to perform.
Exactly. But with DRL, we can shift from this explicit programming to implicit learning. Instead of telling the robot exactly what to do, we provide it with a goal and a reward system, and it figures out the best way to achieve that goal on its own.
So it's like giving the robot a problem to solve and letting it figure out the solution through trial and error.
Precisely. This learning-based approach requires less human intervention and can significantly reduce the cost and time involved in developing and deploying robots.
That's a real game changer for industries that rely on automation. It makes robots much more accessible and opens up a ton of new possibilities for their application.
Okay, so we've covered robotics, but what about other fields? I know you mentioned finance and healthcare earlier. Can you give us a glimpse into how DRL is being applied in those areas?
Certainly. In finance, DRL is being used to develop algorithmic trading strategies that can adapt to those constantly changing market conditions. These algorithms can analyze vast amounts of data, identify patterns, and make investment decisions with speed and precision that often surpass human capabilities.
So it's like having a super intelligent financial advisor that can process information and make decisions much faster than any human could.
That's a good analogy. And in healthcare, DRL is showing a lot of promise in areas like personalized medicine, drug discovery, and even robotic surgery. For example, researchers are exploring the use of DRL to develop personalized treatment plans for patients based on their individual medical history, genetic makeup, and lifestyle factors. Wow, that's truly personalized healthcare. Tailoring treatments to each individual's unique needs. It sounds like something out of science fiction.
It is cutting-edge technology, but it's becoming increasingly real. DRL is also being used to accelerate drug discovery by helping researchers identify promising drug candidates and optimize their development process. And as we touched on earlier, robotic surgery is another area where DRL is making significant strides.
It's amazing how DRL is being applied to such a wide range of fields, from robots that can fold laundry to algorithms that can personalize medical treatments. But I'm curious, with all these advancements, what are some of the key challenges that are still holding DRL back from reaching its full potential?
That's an important question. Despite its impressive achievements, DRL still faces a number of hurdles that researchers are actively working to overcome. We've already discussed sample efficiency and generalization, but there are other challenges as well.
Okay, let's delve into those challenges. I think it's crucial to understand both the possibilities and the limitations of this technology.
Absolutely. One of the challenges is the issue of reward design. In DRL, the agent learns by receiving rewards for desirable behavior. But designing effective reward functions can be tricky, especially for complex tasks. If the reward function is not well designed, the agent may learn to exploit loopholes or find shortcuts that don't actually align with the intended goal.
So it's like giving the agent the wrong incentives, and it ends up learning the wrong lessons.
Precisely. It's like training a dog with treats, but the dog figures out how to get the treats without actually doing the trick you wanted it to learn.
That makes sense. So designing the right reward system is crucial for making sure the DRL agent learns the desired behavior. What other challenges are there?
Another challenge is safety and robustness. As DRL agents become more sophisticated and are deployed in real-world applications, it's crucial to ensure that they operate safely and reliably. We need to make sure that they don't make decisions that could harm humans or cause unintended consequences.
Especially in areas like self-driving cars or healthcare, safety is paramount. How are researchers addressing this challenge?
Researchers are developing techniques to ensure the safety and robustness of DRL agents by incorporating safety constraints into the learning process, testing them rigorously in simulation and controlled environments, and developing methods to monitor their behavior and intervene if necessary.
So it's like building in safeguards to prevent the AI from going rogue. What other challenges are there?
Another area of active research is interpretability. As DRL agents become more complex, it becomes increasingly difficult to understand why they make the decisions they do. This lack of transparency can be a barrier to trust and adoption, especially in those high-stakes applications where we need to understand the reasoning behind the AI's actions.
It's like having a black box that spits out decisions, but we don't know how it arrived at those decisions. That can be unsettling, especially if those decisions have real-world consequences.
Exactly. Researchers are working on developing techniques to make DRL agents more transparent and interpretable so we can understand their decision-making process and build trust in their capabilities.
It sounds like there are a lot of exciting challenges and opportunities in the field of DRL. But before we wrap up this part of our deep dive, I want to circle back to something you mentioned earlier, the future of DRL.
Ah, yes, the future. That's where things get truly fascinating.
I'm all ears. Tell me, what are some of the emerging trends and future directions in DRL research?
Okay, so we've talked a lot about the technical side of DRL, its potential benefits, and even the challenges it presents.
It's quite a journey, isn't it? From those foundational concepts to those really complex real-world applications.
It is. But now I think it's time to bring it back to our listener. We always want to make sure our deep dives are not just informative, but also provide something valuable that our listeners can take away.
Absolutely. I think one of the key takeaways here is that DRL is not just some abstract concept confined to research labs. It's a technology that's already having a tangible impact on our world, and it's only going to become more pervasive in the coming years. Right, and it's not just about robots taking over the world, like in those sci-fi movies. DRL has the potential to revolutionize everything from healthcare and finance to transportation and education.
Exactly. And it's important for everyone, regardless of their technical background, to have at least a basic understanding of how this technology works and its potential implications.
So that brings us to the resources we've gathered for this deep dive.
Oh, we have a great selection for this one.
We do. First up, we have that classic textbook on reinforcement learning. It's considered the go-to resource for anyone who really wants to get into the nitty-gritty details.
It's a bit dense, but it's definitely worth the effort for those who are serious about mastering the fundamentals.
Then we have two articles that offer a more accessible overview of DRL. One explores the exciting world of DRL-powered robotics. Imagine robots that can learn to perform delicate surgical procedures or assist with search and rescue missions in dangerous environments.
It's pretty mind-blowing stuff. And the other article delves into the ethical considerations surrounding DRL. It's crucial to think about issues like bias, fairness, and the potential impact of this technology on society as a whole.
Right, because with great power comes great responsibility. We want to ensure that DRL is used for good and that its benefits are shared widely.
Absolutely.
So we've got resources for the technically inclined, those fascinated by real-world applications, and those who want to ponder the deeper ethical questions.
We've tried to cover all the bases.
And now, as we wrap up this episode, I want to leave our listeners with one final thought to chew on. We've marveled at DRL's ability to learn and adapt, but what happens when these AI agents start to surpass our expectations? What if they begin to solve problems in ways we never even imagined or develop strategies that we don't fully understand?
That's a really thought-provoking question, and I think it highlights the need for ongoing dialogue and collaboration between AI researchers, policymakers, and the public.
Exactly.
Sure.
We need to ensure that as we develop these powerful technologies, we do so in a way that aligns with our values and benefits humanity as a whole.
Well said.
And on that note, we'd like to thank you, our listener, for joining us on this deep dive into the fascinating world of deep reinforcement learning. We hope you found it informative, inspiring, and maybe even a little bit mind-bending. We encourage you to check out the resources we provided in the show notes. Continue exploring, stay curious, and keep those deep thinking caps on. Until next time, happy learning.